Hello everyone. Today we're going to learn 10.4, which is area and length in polar coordinate. So firstly, you can take a look at the graph. Here we have a region bounded by the function. The function is given by polar coordinate. R equals f theta, and the theta is from alpha to beta. So in this case, like this shaded region, how to find the area? Okay. So firstly, let's take a look. We're going to introduce the formula of the area by this way. Same as before, when you learn the integral of, when we calculate the area under a function from a to b, we say this integral from a to b fx dx. That's the area, right? How do you find this one? In calculus 1, we did it this way. We cut this into small pieces. And we say each small piece, we take that out. And we treat each small piece as a rectangular, like this. And the length, base of the length is delta x. And height is fxi, which is the height, okay? xi. And then we did Riemann sum. So this is rectangular area, which is fxi delta x I from 1 to n. And if we make n goes to infinity, that means we cut this into small pieces as small as possible. So the limit is just give us the area of the region. Okay, and in this case, we write down this as definite integral. That's definition for Cartesian function, right? In the Cartesian coordinate. Now we are going to do the same idea, but we are going to cut in different way. We are going to cut in this way. Okay, you can see. So each small piece, the angle, we say delta theta. So right now, I'm going to take the small piece out, like this, and draw this a little bit larger. Okay, this may be a small curve. But you know, when the piece is very, very small, the curve is almost just a straight line. So we can draw this up. It's just a little curve, but it looks like a straight line. So we are going to use this. We say this is the area SI, and we use a straight line to approximate this small curve because the piece is small. So that's why it's almost straight. And then right now we get a triangle. Is that right? So what's the area of this triangle? For the triangle, we know that is 1/2 the base times the height. The base length, actually. Okay? And the height, here we know, we say this is Ri because it's just like the root. For function, here this function is r equals f theta. Is that right? So before we have the height is fxi. So right now we have ri. Okay, ri is the height. And let's see what's the base. For a fan shape, okay, before we learned for a fan shape, the length here, L equals r theta, right? So this is the formula for L. So here we say the length, the base length, which is R, I, and what's theta here? Delta theta. Right? Okay, so right now let's write down our SI, which is 1/2 Ri delta theta times another Ri. So we can write down this as combine the Ri together, Ri squared delta theta. That is small piece area, right? So the whole area equals what? We make the sum and we take the limit. Totally same as before. N goes to infinity. This is the Riemann sum. And here we have, okay, I can write down one more step. Sum of the small si, which means and n goes to infinity, and Si is 1/2 Ri squared delta theta. And if we want to write down this as integral, okay, so delta theta becomes d theta, and theta from alpha to beta, and this is 1/2, and we change r into just f theta squared. Okay, so this is the formula for the area. Let's write down this as A. Okay, usually we use as for surface area, right? So this is just the area for the phi shape. Or you can write down just like alpha to beta 1/2 r squared d theta. Either way, they are the same thing, right? So now let's write down the formula in a better way. So we can also take the 1/2 out because it's constant. But let's just write down this. Okay, let's box the formula. And now let's take a look at the example, how to use this formula to find the area for a curve in polar coordinate. Find the area of the region enclosed by the cardioid, which is r equals to 1 plus cosine theta. So in the last section, we sketched the graph of this function, right? Kind of. We don't have 2 in front, but similar. And this graph, I'm going to draw the graph to you. You don't have to know the graph, but sometimes if the boundaries are not given, alpha, beta, so we should know. You can use calculator to draw the graph. R equals to 1 plus cosine theta. This is the region of the R. There are 2 ways to do this problem. Okay, I'm going to show you 2 methods. Method 1, this is totally symmetric, right? You can either do 0 to pi. So the whole boundary should be 0 to 2 pi. Okay, 0 to 2 pi, whatever the formula, d theta. Or you can do 0 to pi, that means only the top half, and then times by 2. They are the same thing. Okay, you can double check the answer. We should get the same answer. But let's try just 0 to 2 pi now. Okay, when we draw the graph, so start from here, 0. So we have the start from this point, and when it's get 2 pi, it's come back to here. Okay, so the area equals what? 0 to 2 pi, 1/2, and let's see, function square, and the function is 1 plus cosine theta square, and then d theta. So right now, just copy the f theta, right? 0 to 2 pi, and here we get 4. 2 square, which is 4 divided by 2, we get 2, and 1 plus cosine theta square d theta. This, we have to evaluate this by using, the trig function identities. So let's see, we need to simplify. I like to take the 2 out because it's constant and expand the square thing. So it's 1 plus 2 cosine theta plus cosine square theta d theta. Okay. And we said for the square thing, we need to decrease the power by using double angle formula. 1 plus cosine theta plus, half. 1 plus cosine 2 theta d theta, right? And you can combine the 1/2 and the 1 together, simplify. So which is 3/2 plus cosine theta plus 1/2 cosine 2 theta d theta. So here I just combine the constant, those 2 together. And now let's evaluate this integral. 3/2 theta. Is that right? And what's the integral of Okay, so here we still have 2. Sorry, I missed the 2 here. So sine integral, cosine integral is sine, right? Plus 2 sine theta. And here, cosine 2 theta integral should be sine 2 theta over 2. And we have another 1/2 in front, so 1/4 sine 2 theta. And theta from 0 to 2 pi. Okay, 2 is in front of everything. And we know sine 0 and sine pi, 2 pi, they both, 0. We can just ignore those 2 terms. So basically it's 2 times 3/2 theta times, change theta into 2 pi. Simplify. So the answer is 6 pi. Okay. So this is the example. We just use the formula, right? And evaluate the integral. Now let's take a look at this exercise problem. The exercise problem is given just by the graph. So let's take a look. Here, theta is from, this is power 4, okay? And here is power 2. And the region is this one. We are going to write the boundaries for theta later. So r equals 2 sine theta. Actually, r equals 2 sine theta, we had this in the quiz. If r equals 2 sine theta, if we times r by both sides, that becomes r squared equals 2r sine theta. Do you still remember how to change this into Cartesian? X squared plus y squared, which is 2y. Is that right? And then we change this into circle by complete square. So actually this is circle. Okay, that's why I draw like this shape. Now we can say, what is theta? Pi over 4 to pi over 2. If our region is like this part, then theta from 0 to power 4, right? So just be careful of the region. Now let's set up the integral. The area equals pi over 4 to pi over 2. 1/2 r squared, so which is 4 sine squared d theta. Evaluate. I'm going to take the 2 out. And sine squared is 1 minus cosine 2 theta over 2. And we can simplify 2 and 1/2 now. And let's see. 2 and 1/2 cancel out. Power 4, power 2. 1 minus cosine 2 theta. So we can make this integral a little bit easier. Now the integral of this one should theta minus sine 2 theta over 2. And theta from power 4 to power 2. Okay, and if we plug in power 2, so pi over 2 minus sine, actually power 2 times 2, so it should be sine pi over 2, and then minus, okay, plug in power 4 minus sine pi over 2, now divide by 2. Okay, and sine pi is 0. And the pi over 2 minus pi over 4, which is pi over 4, and the minus 1/2. And actually it should be plus, because minus minus becomes plus, right? So that's the final answer for this problem. Okay. Now let's take a look at another one. This is the basic example, but sometimes our region is bounded by 2 curves. So let's see. It's like in calculus 1, if the curve bounded by one function, we just use the formula integral from a to b fx dx. If we have function bounded by 2 curves like f and g, so how to find that region? Okay. In that case, that's f minus g, right? An integral. Find this area. Okay. Area of the region that lies inside one curve. R equals 1. So you know what is R equals 1? All the radius equals 1 is circle, right? and outside of R equals 1 minus cosine theta. Okay, so this region is bounded by two curves. I'm going to draw the graph to you. So 1 minus cosine theta is this one, cardioid. Okay. And the circle is R equals 1. So the graph looks like this actually. Okay, you can use calculator to draw the graph. Now let's shade that region. What you are looking for? Inside the circle and outside the cardioid. So should be this region. Okay. And from the graph, we can see what's the boundaries for theta, negative power 2 to power 2. You can do another way. You set those two are equal to each other. 1 equals 1 minus cosine theta. You can see in this case you get what? Theta, cosine theta is 0. That means theta is plus minus pi over 2. Okay, you can double check. And also later we will have more complicated circle. How to find the intercept? It's just like make those two functions equal to each other. For this case, we make 2r equal to each other. So in calculus 1, we make a 2y f equals g and solve for x. All right, that's how we find the intercept. So let's see. Now we have the boundaries, and actually the error equals what? For this one, the error equals, can take the 1/2 out. Okay. So the boundary should be negative power 2 to pi over 2. So we can say we use the larger, the outside this region, the area, and then minus the inside area. And then we get the middle part. So we can say, can RR squared minus R1 squared d theta. Is that correct? Because it's like a kind of like integral of R2 squared d theta. That's the outside area, and then minus the inside area. And then if we combine them together, which is that one. Okay, 1/2 R2 squared minus R1 squared. And let's change them into R2. What is R2? R2 is the outside one. Who is the outside one? That is the circle, which is R equals 1. And R squared is also 1. Okay. And what is R1? That's inside. So which is 1 minus cosine theta squared. Okay. And d theta. Let's simplify. A lot of calculation in this section. One half negative pi over 2 to pi over 2. So here expanded the square thing. So 1 and then minus 2 theta because we take off the parentheses. So plus 2 cosine theta and then minus cosine square theta d theta. Right? So 1 and the 1 can cancel out. Negative power 2 to power 2. 2 cosine theta minus cosine square theta d theta. So for this problem, we also have two methods to solve. You can double the region from 0 to power 2. Right? So 0 to power 2 is half of the region, and then double it. We get the whole region. Or you can look at this function. This is even function. Is that right? Because cosine negative theta is just cosine theta. Even function. So in calculus 2, we have property if we have symmetric limits for the even function, we can change this into the properties like this. I'm going to write down here. Negative a to a fx dx equals, if function is even, this equals 2, 0 to a fx dx. If it's odd, if the function is odd, it's just 0. Do you still remember this in calculus 2, this property? And the best example, think about the x squared, x cubed. X squared is even function. X cubed is odd. So for the even function, for example, if we have negative 2 to 2 f dx, so this equals 2 from 0 to 2 f dx, right? So because double of like 0 to 2. And here, if we add those two together, one positive, one negative, which is 0. So we learned that in calculus 2. And here we want to make the integral a little bit easier, so I like to change the limits into 0 to power 2 and double it. But you can also do this at the beginning by just looking at the graph. You can do either way. Okay. And now evaluate this. 2 cosine theta minus, so same thing, we are going to use the double angle formula, d theta. And it becomes, the integral of this one will be 2 sine theta minus 1/2 theta, and it should be minus 1/4 sine 2 theta, 0 to power 2, right? And the sine 2 theta, actually, if we look at this term, sine 2 theta, when we plug in bounds, it will be sine pi and 0. So both are 0, so you can just look at that as 0. So this becomes 2 sine power 2 minus 1/2 times power 2, right? And then we plug in 0 bound, all the terms, those two terms both will be 0, so we don't have to write down them. So 2 minus pi over 4 is the final answer for this problem. Okay, so this is the area of the. Okay, so some of you may be confused why, how do we find the area bounded by two curves? If I draw in this way, maybe that's a little bit easier for you to understand. Okay, this is R2. Okay, R2, the function. The inside is R1. So the area bounded by those two curves should be A2 minus A1. So the outside minus inside, right? So the outside is 1/2 R2 squared d theta, and then minus 1/2 R1 squared d theta. And if we combine, R2 squared minus R1 squared d theta. So in the future, you can use this formula. Oh, you don't need to memorize, we always just use the outside area minus the inside, we can get the middle part. Okay. And then now I'm going to give you one like a kind of exercise, but I just want to help you to show you how to find the intercept of those two curves. So this question wants us to find the region inside this circle and outside of 1 plus sine theta. Okay, so the graph looks like this. R equals 3 sine theta, which is a circle, look like this. And cardioid 1 plus sine theta, which is also heart shape, but the heart looks like this. Okay, and now we want to find the region inside the circle, outside the cardioid. Should be this one. Okay, so for this case, you can see the angle. We don't know what's the angle here. It's hard to see, right? So I'm going to draw like this and this. So we need to find those two angles. How to find those two angles? we set those two r equal to each other. So it's like we let r equals, we let 3 sine theta, r2 equals r1. 1 plus sine theta, solve for theta. Let's see how to solve it. So this gives us 2 sine theta equals 1. Sine theta equals 1/2. Is that right? So theta equals what? Sine what is 1/2? Or you can say sine is like inverse of that one, right? But you can think sine what is 1/2? Sine pi over 6. So here should be pi over 6. And you can see because symmetry, the other way, so this is actually 5 pi over 6. Okay, so our theta in this case, it should be pi over 6 to 5 pi over 6. But when you evaluate the integral, you know, I don't like to use those boundaries. I'm going to use double of like a pi over 6 to pi over 2 because I always like pi over 2. Pi over 2 is better than the other one, right? So double that region, that is better. So I'm going to write down the formula for you. Double of this one, and it should be 1/2 r2 square r2, which is outside 1. Outside should be circle, and minus, and then evaluate this integral. Okay, so here just give you some idea how to find the intercept of two circles, two curves, and also how to, you know, make the calculation a little bit easier. Actually, I think this is one of the homework problem. Okay. Let's take a look at the formula for arc length next.